AP Calculus students, how you doing today? We're working on section 1.5. Section 1.5 in your book is named Infinite Limits. I think this is a very, very poor name because take a look. This is like jumbo shrimp, right? Jumbo and shrimp. This is limits we know have to have a real value, and if they're approaching infinity, then there's not a limit. So for them to call it infinite limits, I think is totally misnamed. Here's what's actually happening here. This should be called limits that do not exist because they are unbounded at x equals c. So what's going to happen in this section basically is these limits are going to not exist, but we're going to explain why. Are they heading to negative infinity or positive infinity? So let's take a look at our notes over here. You've already studied the limit as x approaches c of a function equals plus or minus infinity, and so does not exist. We already studied this in pre-calc. It is called a vertical asymptote. So if you remember, when you had a rational expression like here or like here in pre-calc, and even in algebra 2b you studied this, if there was an x that you put into the denominator and it made the denominator 0 and did not cancel, you could not simplify it, what we found is that's where a vertical asymptote was located. Well, now in calculus speak, right, we're just saying right here where this vertical asymptote is, that to the left of this x, the graph is approaching negative infinity, and to the right, it's approaching positive infinity, and so there is no limit. We called it a vertical asymptote before, now we're calling them limits. Remember, these limits that create vertical asymptotes that do not exist are due to being non-removable discontinuities. If you remember, we have two other discontinuities that we're not looking at here. That is a removable discontinuity, which creates an open point on a graph. Notice we don't have that here. And also jump discontinuity, which is at an x, the y value jumps between two, usually in a piecewise function. So we are not looking at those today, just infinite discontinuities. So here's what we're going to do. We are going to use direct substitution of a value very close to x equals c, like 1/1000th away, from the left and the right to determine why the limit doesn't exist, to actually say it's because it's approaching negative infinity or positive infinity. So we've learned quite a lot about limits, and so I made this little flow chart of decision making. So here we go. Here's when you are offered a limit, the first thing you say is, can I use direct substitution? And get an answer. If yes, you're done, right? Excellent. What if you can't? No. Then do you have some trig? Can you use the squeeze limit, the squeeze theorem? If yes, you're done. If no, then that means that the limit doesn't exist. Okay? Again, let's go back. What if, can I use direct substitution? No. What if you can't use the squeeze theorem? Can you write a simpler function then? If yes, you write a simpler function, come back around and say, can I use direct substitution? And again, if no, the limit doesn't exist, right? You've tried everything. Okay, so there's a little flow chart of our thinking on limits. Now let's come on up here and notice what we have is these are limits that I already told you they do not exist. We're going to evaluate the limits from the left and from the right and say if it's approaching negative infinity or positive infinity. Okay, so here's what I'm going to do. I am going to use direct substitution of a number, a value that is very close to 2 from the left. I'm going to call that 1.999, and I'm going to put it right here. Okay, now notice no matter what here, the numerator is positive, right? Notice in the denominator here, 1.999 minus 2 is a very small negative number. 1 divided by a very small negative number approaches negative infinity. Again, just imagine that instead of 1.999, I put 1.999999999 minus 2. Notice I would have 1 divided by an infinitely small negative number, and 1 divided by a number very close to 0 and negative is negative infinity. So we're saying why that limit doesn't exist. Let's do that over here. The limit as x approaches 2 from the right. That would be 2.001. Notice again that the numerator is positive, and when I subtract in the denominator, I get a very small positive number, right? And so 1 divided by a very small positive number, very close to 0, is positive infinity. And so this limit doesn't exist as x approaches 2 of 1 over x minus 2. And here's the reasons why. And what you could do is you could actually graph this in the calculator. 1 over x minus 2, it has these 2 branches here, right? And it's been moved to the right too. So you can pop that in and see if you are correct on your assessment here. Let's take a look here. The limit is x approaches 2 from the left of negative 1 over x minus 2. Notice here, the only thing that's changed is now the numerator is negative, where before it was positive. Otherwise, everything is the same. So that means it's going to change the sign of negative infinity to positive, and from positive infinity to negative infinity. Again, that means the limit as x approaches 2 of negative 1 over x minus 2 does not exist. Okay, let's take a look here. The limit is x approaches 2 from the left of 1 over, and this is x minus 2 squared. Just so you have practice again, let's go ahead and pick a number very close to 2 from the left. There we go, 1.999. Notice that the numerator is positive. 1.999 minus 2 is a very small negative number, and when I square it, it becomes positive. There we go, positive infinity. Just giving you some practice here on substituting in small numbers close to your C value. 2 from the right would be 2.001. Again, our numerator is positive. When we put in 2.001, we get a very small positive number. When we square it, it's positive. And so again, the limit on the left and the right of 2 is infinity, which explains why this limit doesn't exist. Okay, I just want to back up though and say we did too much work here. I just want you to know that I did it, so that you would have practice inputting these small values, but the numerator is always positive here, and because you're squaring the denominator, isn't it always positive also? We actually knew that these were both always going to be positive. In case you're confused why 1 divided by, or any constant divided by a very, very small number approaches infinity, let's just look at that over here. Let's do 1 divided by 1, that's 1. Let's do 1 divided by 0.1, right? How many 0.1s are in 1? Right, this is 1/10, there's 10. Let's do 1 divided by 0.01, that's 1/100th, right? How many 1/100ths are in 1? 100. So you can see when you divide a constant by a very small number, I could get smaller and smaller, right? Then that value is going to approach infinity. So you may have already known that, but just in case you had forgotten that. Okay, I'm going to erase that. Okay, now let's find the vertical asymptotes of these different functions here, and then we'll do one more limit. So when they ask you for the vertical asymptote, right, that would be the x equals c that makes this function undefined, and it has a vertical asymptote or a limit that approaches positive or negative infinity there. Now it's the same thing. We know that that's an x that makes the denominator 0 and does not cancel. So let's find where that is. Here's my numerator. My denominator, I can factor x minus 2, x plus 2. I don't have any canceling I can do. Please don't think you can cancel those. That's very, very illegal math. I would have you arrested. Well, not really. I would talk with you about it and maybe feed you a cookie. But those cannot cancel out. If you want to know why, we'll talk about it. But you can see x minus 2 does not cancel, right? There's not the same factor in the numerator or in the denominator. So this means where x is 2 and where x is negative 2 is where the vertical asymptotes are. Let's look here. Find the vertical asymptote of x minus 3 divided by this expression here. Okay, let's do some factoring. Here's our numerator. Here's our denominator. Two numbers that multiply to a positive 3 and add to a negative 4. There they are, x minus 1, x minus 3. So notice that these two factors cancel, meaning there is not a vertical asymptote at x equals 3 because it was removable. Vertical asymptotes only occur at x's that make the denominator 0 and are not removable. So this occurs at x equals 1. Let's take a look here. Negative 4x. And let's go ahead and factor the denominator. X squared plus 4. That must be x minus 2, x plus 2. Let's see. Well, that can't be right. When I multiply a negative 2 times a positive 2, I get a negative 4. That can't be right. Okay, well, they must both be positive then. Okay, let's take a look. That would be x squared plus 2x plus 2x is plus 4x plus 4. Okay, that's not this. That does not multiply out to that. Well, is it two negatives? What is it? No, that won't work. X squared on the outside negative 2x, on the inside negative 2x, and I have a negative 4x. That's not working. And that's because, class, you cannot factor x squared plus 4. They will do this to you on the AP exam. If you did a retake memorization quiz, I did that to you there. This does not factor. And in fact, when you look at it, there is no way to make this denominator 0. There is no vertical asymptote here. Take a look logically why. X squared plus 4. If I need that to equal 0, that means x squared would have to be negative 4. Right? Negative 4 plus 4 is 0. There is nothing I can square to get a negative 4. This cannot possibly be 0. There is no vertical asymptote. Let's look at the last one. Find the limit as x approaches 0 from the left. Let's call that a negative 0.001. Okay, notice on the x squared we can use direct substitution of a 0. Here's my minus, and 1 over a negative 0.001. Notice minus a negative becomes positive, and this value is approaching infinity as I get closer and closer to the left of 0, right? And so now I have infinity. I did this one because it tends to mess students up with that negative there, but you have two negatives make a positive. And so that is our section 1.5 for infinite limits. Have a great day.
Have a good weekend.